Hello, my name is Flavio, and I will talk a little bit about Industrial IoT and NetX. So, I, the, I start talking a bit about myself, and then I will talk about a recent design that I've been working on, which is an IoT gateway. I will pass through all the stages of the design, including hardware, NetX, and application software, and some of the results and the lessons learned from this project. I'll start off telling a little bit about myself. My name is Flavio again. I'm an electronic engineer from Brazil, from Campinas. I had a diploma on the electronics and communication systems from École Centrale de Lyon. It was an interchange program during 1 year in France, and the past 20 years I have been working on embedded systems design, embedded software development for several different industries, several different technologies. I worked with Linux, embedded Linux, PC Linux, and microcontrollers, STM32, microchip PIC, and some FPGAs. And from the last 13 years, I have been working on Fire Innovations, where I'm the founder of the company, and it is a Brazilian design house company, a company where we are contracted to design hardware and software to be included on other products. So this presentation intends to tell my experience on designing my product. In fact, it is a project that it was initially supposed to become a product for the company, and at the end, this project became a platform for projects instead of a off-the-shelf product. and I will pass from the designs, from the decisions that we have taken to implement, and all the hardware parts, and the firmware for this product. It was not initially implemented in NetX. It was finally implemented in NetX. So the version 1 was using bare metal, using FreeRTOS, and our last version of the firmware recently developed was done using NetX. And I intend to describe a little bit about how NetX impacted on our development here. Here's the hardware architecture for the software, not for the product, sorry. And as you can see here, it is a hardware. I need to use the STM32 microcontroller, and a lot of devices peripherals were connected to this hardware, namely the Ethernet. It has Ethernet support, the RS485 support also, and USB as USB device. It has some LEDs for operation indication. The hardware has 2 digital inputs protected by optocouplers. It has 2 analog inputs, also for using operation amplifier for signal purpose management. We have an UART for a console, and in fact, initially it was designed for logging, to see the behavior of the firmware. Now it is used for nutshell and so on. The hardware has also an RTC, a temperature sensor. Another important component of the software is the data flash, or an external flash interface, where we use it here as a hard drive, similar on a hard drive. And the other communication technologies implemented on this hardware are Wi-Fi and mobile device, mobile communication 2G, GPRS model with support of two SIM cards. And finally, the hardware has also an SD card, and this SD card is used for, it's not so much used because but it has the same approach as today we have for the data flash. Initially, the data flash was thought as for parameters and small things, and at the end it was the real final hard drive of the solution. And we had used this SD card as an expansion. Here is a picture of the board. Here we have here the USB, the LEDs, and the Wi-Fi, the GPRS, Ethernet. Here RS485 inputs, power, and below we have the SD card connector and the SIM card connectors too. Like I said, the main microcontroller, the main CPU of the project is the STM32F417, which is a very powerful microcontroller running 168 megahertz and with a fair amount of flash of 512. The Wi-Fi model is the ESP8266, and the GPRS model is the Sierra Wireless HL6528. And the data flash, it is flash SPI with 1 MB storage. I would say that these are the main components of the product and of the project, and where we have worked on Netix too. And how is the purpose of this gateway of this project? The main feature, the main purpose is to become a gateway between devices connected to using which supports Modbus protocol, and deliver the information from these devices to an IoT platform using MQTT protocol. So it has two things. So the gateway connects, for instance, for PLCs or meters, and in using the and regarding PLCs, it acts. It is configured as a slave, and working as a slave, the PLCs update internal tables from the gateway, and these tables are periodically sent to external servers using MQTT protocol and network connectivity, internet connectivity, and from the other side, from the external services, you can send messages to the gateway using MQTT protocol, which will update the internal tables and Modbus tables inside the gateway, and the gateway will make available these informations by the PLCs, which will request this information periodically. This is one use case. Another use case is when the gateway works as a master, when it is responsible to read several different meters and devices which are uh, Modbus slave. So the most common use in our case here is power meters. So if you have a facility running several power meters, you can use the gateway to scan out those meters, collect this data, collect the data, and store it internally, and periodically send all the recorded information to an external server running MQTT. So these are the main features of the product. Initially, thought for it, and as it has also digital inputs and analog inputs, the same behavior, the same for that we have for meters, we have also for these inputs. So we can define periodically reading for the digital inputs, include real-time reading and also pulse counting, and then these values are stored internally for later being exported and published to MQTT brokers and IoT platforms outside. So that's the main purpose, the main for the design for the product. So how we started, and so the firmware was implemented in there are two firmwares in fact inside the board. One firmware is the bootloader, and the second firmware is the application, and we have also to consider the data flash, because here the data flash is really considered as an analogy for a hard drive. So all the configurations and the information and the data of the running software is stored inside the data flash. I used the little FS file system for the project instead of the Smart FS, which is the standard for NUTIX. The reason for that is that I have already worked with little FS in the past, and also because the bootloader they supported the little FS even before they started the code development in NUTIX. So here the logic is that the firmware somehow captured from outside the file and store it on the data flash, and this file is the new firmware, and when the system starts, when the bootloader check if there is a file with a specific name on the data flash. If it exists, then the software is updated, the firmware application is updated. Otherwise, the software is bootloader starts the firmware directly. So to have this feature implemented, I needed to have support for little FS in both applications, so bootloader and firmware. So to have the file system, and the file system that has the support little FS, as far as I knew at the moment to work on that. And it was pretty nice to work even Smart FS or little FS on with NUTIX, because it was really straightforward. I had nothing I didn't need to do anything on regarding specificities. So I just changed the option and it worked. It just worked for the application. So here now I'm talking a little bit about the NUTIX, and in this case I will why I choose NUTIX to work on the project. I choose NUTIX because I would like to have something that was quite complete in the sense of hardware support for my board. So not not just a scheduler just like FreeRTOS, and then I had to mix with the how features provided by ST, but I would like something that alone itself it had everything. So it's just like an operating system itself. So just like the Linux or Windows in our PC, I would like something similar on the firmware because as the base, and on a open source way that I could count on and be part of a community to support to support and have support. And in this case, Nutanix appeared to be an excellent option. And when I tried and I could execute it a bit, I realized that it was the best option for my project. And one of the things that I liked a lot is the close similarity to Linux. So I have been using Linux to software development for so many years, and then and have the opportunity to work just like that in a firmware was very important for the project and for me, and even for expansion for the software for other targets, things like that. And it was great when I found out Nutanix, and then that's why I started to work on that since on. And in our case here, the board was pretty close. The microcontroller is very close to the microcontroller used on the STM32F4 Discovery board, which is a board very used on Nutanix for testing and development and documentation. And then I started from there. So in fact, it was not me. I contracted another person, to Oliver, to start this work for me, and he is a very skilled Nutanix developer too. To know he is, I'm not sure if I am, but anyway, he is a very skilled Nutanix, and he implemented all the initial bring up the board support functionalities for my board for me, and which includes Ethernet setup and SD card support, USB, UART availability, IOs, integrating the data flash, because we know that even if the board is closed, there are a lot of very different configurations and this work must be done, in fact, to have this and now integrated. For at the end, we have a flawless nutshell boot, where we can use small simple commands to access the peripherals, such as USB, such as SD card, Ethernet, and Internet, and also the Wi-Fi and GPRS modules. So yeah, and during this process, I followed up with him, and I realized that the board support is not hard to do here. In this case, it is not so much low level. It is a bit low level, but it's not so much low level. It is for a person who is used to work on firmware and ST basic stuff. It is not critical to, and the code has a lot of layers with a very good naming, the Nutanix source code, so it is very easy to find yourself there and to see how to address these board support implementations. Now that this is the first step for Nutanix, let's say, the second step is to prepare it to implement my project. Nerdix is nice because it has several different approaches that you can do to that, and it is important to choose one. Yeah, I chose it for this project to work on C++, and I chose it to. I would like to have a programming experience similar to an ordinary microcontroller. So I would like to create some kind of main thing, and then I run this main thing, and it is okay. Let's say it's more close to Linux. So okay, we create a code in Linux. So we start with a main, and we compile, and we execute, and we debug. And I would like to have this programming experience in Linux for the board, initially for myself and later for others. And how I used Linux to have that. I used C++. In fact, it was not mandatory, but I would like. I've been working with C++ project in the past quite a lot, so that motivated me to work on a firmware on Linux. And I deployed Linux as a library. So okay, it seems strange to have the whole operating system is a library in my project, but it's okay regarding firmware development, and that we will have just a single image to be installed on the microcontroller every time that we will execute for testing. It is not something that is there and then you change an application, so every time you have to load everything, so it's not a problem to see Linux in this way. Running, we can see the difference, but in development not so much, so that's why I choose that. And another thing is that another important point here is that while compiling, I didn't need to compile Linux every time, and don't count on changes on that, but it is not so relevant. So on other approaches, it won't impact either. I created a CMake file structure for my project, and I disabled Nutshell because I would like to see, just like an ordinary firmware, I would like to see my software output from the console, not the. And I didn't want to have a prompt to start my application. That's the purpose, to have a similar a similar user programming experience as a standard Linux application. And I would like to have tools to ease my development. So I used Visual Studio Code. I used Sager JLink for flashing and debugging. I used the Sager tools here integrated with the Visual Studio, and also with the binary generated by my CMake, and it works very well. It was not exactly plug and play. I needed to learn quite some things here, but I have a ST-Link to device to load and debug, and I needed to learn how to set up all of this, but it was fine, and then I have a complete working environment for my project like that, and it was pretty awesome. And regarding the project itself, now starting to say a little bit about the implementation. I used external libraries. Some libraries came directly from the Nutix configuration. Other libraries I added as CMake components in my build. So I don't remember. By the time I was preparing the presentation, I didn't remember, and I couldn't see which libraries I used from the Nutix. So, but I remember that I used the JSON. So I listed JSON, and the others I remember that it was on the code, which were libmodbus and embed TLS and MQTT-C. This the first one to provide my Modbus communication, the second one to provide the secure communication over MQTT, and the latest one here, the MQTT-C, to provide the MQTT-C protocol in Nutix. It was almost directly to. In fact, libmodbus didn't have support to CMake, so I need to create the CMake file myself. But the others, the CMake file from the open source project was quite straightforward to connect to integrate to my project. And now here I have a small brief overview of my project. So these are the base classes from my project, where the Phi gateway is the main class, is the class that starts everything and launches everything. So my main.c is just to instantiate Phi gateway and run it, and it's called another method called run. And this class is responsible to, inside that we have all these other classes, where status class contains the status information about the real-time operation of the firmware. System data contains all the configuration information used by the gateway. LEDs is just turn on, turn off LEDs and blink. Network interface here, network IF here, it is a, let's say it's almost a virtual object with which has other inheritance, which are the network communications available on the projects. So I have a class called Ethernet. I have a class called GPRS, and I have another class called Wi-Fi. And then all of these are specializations of the network interface class, and this class has all the specification of the services that are used by the Phi gateway class and the others to perform network operations. Mostly here in this case is the socket management and the operation management, detection of failure, things like that. So these are the, let's say on the right side we have these are the support classes, let's call it like that. And then on the below here, the transmission, capture, and manager have operational classes, where transmission is the class responsible to send data and get information from the send information for the MQTT. Uses MQTT as a support object. The capture, in fact, is responsible for the Modbus communication, and also the IOs. So it is responsible to capture the information to the other devices plugged on the gateway. And manager is a class responsible to handle the USB communication. So the USB communication to exchange, it was used as a command. It's for changing and setting parameters on the device. That's the only use of the USB in the project. So so the manager class is responsible for handle this and update the system data, the system data contents. And system data contents is used by every working object here on the project. And here I have a flowchart, a basic flowchart of the main operation of the software. So it is I call it setup here for the beginning. It is just to be some some kind of Arduino analogy for set up all the hardware and the basic software configurations to before real execution, where it is in Arduino is on loop, and here I draw a loop here just after, and in here in my loop here the first thing is to check the network availability, and then the second thing is to check if their commands are arrived from the USB. If there's data from in USB to be evaluated, it will be done here. The next thing is to check if we need to scan data from using the Modbus, and after the scan we have, and then the transmission, the communication with the MQTT is performed. First, the data is sent, and then it check if they're receiving data to be processed, and that's the loop, and then the status are updated, and then it comes back again to the start. So of course that inside of each run here and scan and things like that there are timers that and checks for in case of the manager. We check on the file descriptor if there are bytes there arrived from the USB, which is works just like any other serial. We use the USB CDC implementation here, so it's just like a serial communication standard if we program in Linux. In case of capture, the activities here it executes every time, but the execution inside is based on timers. So we set timers. Okay, if we have to wait 30 minutes to perform a scan, so every time the scan is called, but it will be executed itself only after 30 minutes, and the same happens for transmission. That's the approach. I'm not sure if it is the best one, but it is quite fair, and I would like to have the implementation as simple as possible for understanding from top bottom. And here what I have from all of this, now I have now it is working. The software it is very solid, working with Ethernet interface. We are testing the GPRS implementations. GPRS here it was implemented using the NUTX PPP strategy. And one thing that I didn't realize at the beginning of the project and caused some issues here on this project is that the Wi-Fi, because in fact I checked it, the Wi-Fi there is a library for ESP 8266 support on NUTX, but it is not the way that the correct way for NUTX for that, because the NUTX it implements the networking just like Linux. It has the concept of network driver and the network interfaces. So here we have one network interface for the Ethernet, another one for the GPRS, and I needed another one for the Wi-Fi too. And then I open sockets and then connect or bind and work just like that. And this is not using the library for ESP8266 is not available, which will impact in all my architecture. So So to solve this, so in this case, I let the Wi-Fi implementation on hold, and I started to talk on the community about how to implement it. There is an approach for in Nutanix to implement this. There is I don't remember the name here now, but there is an approach where we have a wrapper. Let's say that it is a network driver wrapper, which is responsible to connect to another driver, where this driver will talk directly with the peripheral to provide the network interface support. And this is the approach that must be done. There is a very nice past presentation describing how to implement that for another Wi-Fi model, and I intend to work on that as soon as possible. And one thing that is important here to mention is the size of the firmware. So the size of the firmware, it took almost all the space available for that, which is compared to my previous implementations, it was quite a lot. But I believe that it was mostly caused by the use of C++, it was not caused by Nutanix. It was caused by C++. And I intend to investigate that in the future, but for now that's the only observation that I could do. And what I learned for all of this is that what I would say is that I don't know if I did it well in case of using to implement as the programming experience similar to an application. Because the code, I started to realize that after the code, I saw the code size. Maybe if I used the standard directory structure on Nutanix and add my application inside the app and things like that, and split the implementation instead of several objects inside a single project. If I used different applications running internally on Nutanix structure and using communication technologies between them, or even a database, or to make the glue between the applications, maybe this could I could have a more simple project. Of course, that I strongly believe that if I implemented this code in C, it would take less space. But I really intended to work on C++. Maybe I need to figure out in C++ how to improve my programming techniques to reduce size. Because one thing that I like it most in C++ instead of C is that I'm not a language geek. I don't know a lot of features and details of the language. I don't advocate for language, but in most of my projects during my life, I worked more in C and more in Python for testing, and sometimes now more recently more development in Python. And the past few years I started to work on C++, and I started to implement algorithms, things like that, and this implementation using data structures, it's much better to do that in C++ than in C. And I don't want to lose that. So we use in Python a lot of the structures. We use a lot of in C++. It's possible to use similar to Python, but it's harder to do that in C. And and I would like to think more when programming. I like to think more on application and the data organization instead of more details, and that's and that's one of the reasons that I chose to work on C++ in this case. Maybe I'm wrong. This is a question. It is a matter of discussion for hours or years. And finally, the driver. So I need to figure out how to do that during my working plan, and I intend to implement this driver support and add it on the code base of Nutix. So I believe that's it. So I would like to thank you for the opportunity and I'm available for questions, whatever you want, and I can help you. I intend to have this project open sourced as soon as possible. I don't know how to do that yet. I need to organize almost everything, and I intend to document it too when it started to become open source. And but that's one of the reasons that I'm presenting here. I'm just showing it overly, but later in a couple of months, probably all of these will be available online. Thank you very much, and see you later.